Okay, so let's take a look at this sample problem. So the figure shows a cross-section of a spherical metal shell of inner radius r. A point charge of -5 μc is located at the distance r, capital R over 2 from the center. So this is the sphere, this is the metal shell, this is the metal shell. And then, of course, this is a sphere, so the center is at this point. And then inside this shell, there is a point charge -5 μc. This charge is not placed at the center. Oh, this is R over 2 from it, from the center point. Okay, so if the shell is electrically neutral, what are the induced charge on its inner and outer surface? So it is electrically neutral, so the total charge should be 0, but there can be some induced inner induced charge on the inner surface and on the outer surface. So as much as the total charge is 0, so there may be a positive charge like this, positive charge on the inner surface, and then the same amount of negative charge on the outer surface. Okay, are those charges uniformly distributed? What is the field pattern inside and outside the shell? Okay, so so here we will try to define a Gaussian surface which is actually inside the shell. So we will consider the shell with some thickness, and then here we try to define the Gaussian surface which is really inside the shell. And then, as I mentioned before, inside the conductor, the E field must be 0 at any point. So for this Gaussian surface, if we apply the Gauss law, so epsilon naught and then integration of E dot dA equals Q enclosed. Okay, so as I mentioned, E must be 0 inside the conductor. So for the whole surface, this kind of flux must be 0. So so this whole thing must be 0, which means that Q enclosed should be 0. So here we can see Q enclosed should include, of course, this negative charge, and also the charge on the inner surface, which means that the Q inner plus this point charge is let's call it Q. Q should be 0, which means that Q inner should be negative Q, which is 5 μc, 5 μ coulomb. Okay, so plus it says plus 5 μc charge on the inner surface, and then as much as the total charge should be 0 on the shell, which means that there should be plus 5 μc charge on the inner surface, and there should be negative 5 μc charge on the outer surface. So the total charge will be 0. So they adds up to be 0 μc. So which matches the assumption. So this is the answer. Because it asks you induced charge on its inner and outer surface. So these two are the answer to it. And then, are those charges uniformly distributed? What is the field pattern inside and outside the shell? Okay, so so this is not really trivial, but it says for the outer surface it is uniform distributed. Okay, as it draw here, so you can see the negative sign are somehow equally distributed on the outer surface. But for the inner part, it is not that case. So you can see these negative charge are closer to the left part. So you can see this part are slightly denser, and for those parts which are slightly sparse. This is not easy to have to have a strong reason why it will like that, but you can somehow imagine, because for this part, the distance from the left part to the negative charge is closer, so there will be more charge attract to that part, but at least there will be some charge there, because if this is quite close to each other, there will be some force repelling each other. So this is difficult. I cannot say why it would be like that. If you really need a very precise charge distribution, you really need some computer software to do so. But for the outer part, it is another phenomenon. We will call it a shielding effect. Shielding effect. So it is like a shield. So which means that if you have a charge outside the shell, just say this is Q0, a test charge, a positive test charge. So this Q0 will see something like what I mean is that this Q0 won't see where this negative charge is. It feels like the negative charge, so it is like negative 5 μc is equally distributed on the shell. So this shell is like a shielding, it's like a shield, 像个盾牌那样。OK， 盾牌啊 ，shield 是盾牌嘛，就是如果你玩游戏玩得多的话，你就知道嘛。OK， so actually this charge outside it cannot really see what is inside. So this shell is just like a shield. Okay, so where these negative charges won't influence how this positive charge or this test charge feels. So it's just like it will generate a uniform, just like maybe it will actually like this charge is at the center. So this is called the shielding effect. If you're interested to this, you can check something called the Faraday's cage. Faraday's cage 就是那个法拉第电笼啊。It feels like this is a metal cage, and then a person is standing inside it, and then there will be some electric field outside, but the person won't hurt. So it's also this shielding effect. Okay, so the cage will generate the E field cancelling the E field outside. So something like that. Okay, so just go to the next part. So here we will try to apply the Gauss law to quickly find some E field generated by some symmetrical structure, some symmetrical 对称 symmetrical structure. So for this one, it is called cylindrical, cylindrical 圆柱对称 Okay, so a section on an infinite long cylindrical plastic rod with a uniform charge density lambda. Okay, so this rod is infinitely long. I'll go to here for infinity long, go to there for also infinity long. Okay, so okay, with a uniform charge density. Okay, so the total charge amount should be infinity, so we can only define the linear charge density because it is a line. Okay, so for the plane it is surface density. Okay, sigma. So here is a linear density lambda. Okay, so the charge distribution and the field have cylindrical symmetry. So to find the radius r, we enclose a section of the rod with the concentric Gaussian cylinder. Okay, so here we try to define the Gaussian surface as a cylinder. Okay, so we have a top face, bottom face, and a side face. Okay, so this is a cylinder because we try to find, for example, the E field at this point or the E field at that point. Actually, the E field on the side face are all with the same magnitude, but point to different direction. For this one, point to bottom right, and for this point to the left, slightly bottom left, and then for that point to that side, something like that. Okay, but yeah, on the same cylinder, yeah, all the magnitudes should be the same. Okay, so we enclose a section with a rod, blah blah blah, and then yeah, the radius is small r, so the radius is this one, and then the height is h. So the h is not really important, so finally it will cancel out, so we just assume a variable h here only. So the net thrust through the cylinder from the Gauss law reduced to something like this. So at the very beginning, the Gauss law looked like epsilon naught integration of E dot dA and then equals Q enclosed. Okay, so no matter what problem, you can really start from this one. And then, so we will try to evaluate or what is this surface integral, and then we will try to count what is the Q enclosed. So for the Q enclosed, it is easy because we try to count the Q enclosed from here to there. So yeah, so something like this. Okay, so of course this height is h. The height of the cylinder is h. So this is h times the density will be the total charge amount between this part. Okay, so this Q enclosed is easy, which will be lambda times h. Okay, so this is the right hand side part. For the left hand side, epsilon is a constant, so we just put it there. And then this is the surface integration, or we can denote it as a capital phi. Okay, so next, yeah, this is a cylindrical, so there are three phases. For the top face and bottom face, you can clearly see that, yeah, as much as this is symmetric, the E field should be in the radial direction. So which means that for the top face, dA is pointing upward. For the bottom face, dA is pointing downward. So dA and E always perpendicular to each other, which means that E dot dA should be zero. For the top and bottom face. Okay, which means that this side and that side won't contribute anything to this net thrust. So the only phase will contribute to the net thrust is the side phase. So for the side phase, and then we can see that E should be uniform, and also E will be parallel to the dA. Which means that this E dot dA integration will be like integration of E times dA, because they are parallel to each other, which means that the angle between them is 0. Cosine of 0 degree is 1. So yeah, so this is nothing but this. And then we also know that E is uniform over the whole surface, which means that E can be fractal out. So it turns out to be E times integration of dA, which is nothing but the surface area of the side face. Okay, so for the area, so it turns out to be E times the total area, which is A. So the area of the side face is easy. So if you try to just cut it out, so maybe let me try to, so this is H. So let me try to just cut it with a scissors, so like this, and then you try to explain it. It turns out to be a rectangle, right? So it turns out to be a rectangle like this side is H, and then this is a circle. This is a circle will be the width of this rectangle. So this width will be 2 pi r. So the area of this rectangle will be H times 2 pi r, which means here A will be 2 pi r times H. So this is the surface area times the E field, which is uniform on the side face, and then also times this epsilon naught. Okay, so epsilon naught E times A. Okay, and then A is this term. Okay, E equals lambda H. So we come to this part already. Okay, so here we can just have some cancellation. This H and this H cancel each other. So the height of this cylinder is not important because this rod is infinitely long. Okay, so we just move over this term and these terms to the right side. So finally we have E equals lambda over 2 pi epsilon naught R. Okay, like this. So this is the expression for a infinitely long rod. I mean the E field generated by the infinitely long rod. Okay, so which is relevant to the linear charge density and also the distance from it. Okay, this is like 2 times k. 2 times k. K is 1 over 4 pi epsilon naught. Okay, so only related to these two variables. Okay, so you can here see that after using the Gauss law, the calculation will be very, very easy. As much as you know how to evaluate this term. Okay, if you don't, you can imagine if you don't use the Gauss law to do the same thing with the method in chapter 22, it will feel like you need to cut it into many slides, many elements, and then you need to do some integration. Probably you can cancel the vertical component. For example, this is ds, this is ds prime. Okay, this ds will generate an E field pointing to that side. So we have dE something like this, and then this ds prime will generate something like this, dE prime. Okay, so the vertical component cancel each other, so that we only need to calculate the horizontal component, and then you integrate from negative infinity to infinity. I don't really know whether you can finish it like this because the integration might be quite tedious. I'm not really sure. Maybe not that difficult, but at least even though it can be calculatable, but yeah, it will be much more complicated than this procedure. So yeah, so this is two things. Okay, if you don't know what is a Gauss law, what is a surface integral, then you need to do separation and then addition with the integration. And here, if you know the Gauss law, then you can just just try to evaluate this surface integral, and then we can come up with an expression very quickly. Okay, so the next one is the planar symmetric. Okay, so here the keyword is non-conducting. Actually, it is not so related. Yeah, but I can say that if sometimes the question may mention this material is conducting, this material is non-conducting or isolator. Yeah, if it is conducting, it means that there will be free electron. There will be free electron for conducting material. The main difference is like there will be induced charge like this thing. So in this question, it mentioned this is a metal shell, so there will be induced charge. But if it is non-conducting, then it will usually assume there will be some specific charge distribution. Then after it assumes the charge distribution, the charge distribution won't change anymore. This is for the non-conducting material. Then the charge distribution won't change later. Okay. Okay, so for here, I don't think whether it is conducting or non-conducting is really important, because it already assumes that it has a uniform surface charge density, and if this plane is infinitely large, and it should be uniform distributed. Okay, so yeah, so here it says we can also apply the Gauss law to this cylindrical, something similar to what we did last time. So here we only have a plane rather than a conductor, So this is a plane. We also consider it is thin, although it doesn't draw very thin. Okay, so because this plus sign is slightly to the right side, it feels like there should be another surface, but actually not the case. You consider this is a thin metal plate. I mean thin non-conducting sheet. Okay, so there are just say sigma to be the surface charge density. It can be either plus or negative, positive or negative. Okay, either are okay. So here we have a infinitely large but thin metal sheet, non-conducting sheet, okay, with a surface density to be sigma. Okay, so here we also apply the Gauss law for this cylindrical. So in this case, we already know that the E field on the right side will point to the right, and then E field on the left side will point to the left, because this is infinitely large. So you can always find symmetric part. For example, for this point, generate by here. So this will be DE like this. And then you can always find the symmetric part to generate the DE prime, which cancel the vertical component. So the E field must point to the horizontal direction. So on the left side, point to the left, right side, point to the right for positive charge sheet. If it is negative charge, the direction of the E field will be the other way around. Okay, so here, so this is a cross section of the cylindrical. Okay, this is a cylindrical rather than a rectangle. Okay, so here for the side face, just say this point DA will be pointing upward. For this point, DA will be pointing out of the page, and then for here, DA pointing downward. Okay, so this DA always perpendicular to the E field. Okay, so for the side face, it won't contribute to the total flux. The net flux. Okay, so only this surface and also this surface will contribute to the net flux. Okay, so here we assume that A is the surface area of this circle. So E times A, E is also uniform. By symmetric, because this sheet is infinitely large. So so for every point, they look at the same thing. Even though we can only draw a finite large, the finite plate, but actually it's infinite. So for this point, for that point, they look at the same thing. Okay, so E should be uniform. Okay, so for this one, E and A point to the same direction, also point to the right side. So this E dot dA is nothing but E times A. So we have E times A, and then for this side also E times A. So for this integration, this is 2 times E times A. Okay, on the right side, Q enclosed is the charge within this part. So the area will be A, and then times the surface charge density. So density times the area will be the total charge in the area. Okay, so on the left side we have epsilon naught EA plus EA, and then on the right side we have sigma times A. So also we can cancel the A on both sides. Okay, finally we can just move over 2. So actually on the left side is 2 times epsilon times E. 2 times epsilon naught times E. Okay, and then we move over 2 epsilon naught to the right side. So finally we have E equals sigma over 2 epsilon naught. Okay. So yeah, so which matches this one, okay, because they are the same thing. Okay. Okay, so this is another example to show that, okay, we can use the integration to find out this expression with the integration, and then we make R to be infinitely large. Okay, and finally we can find this expression, which means that this plate, if it is infinitely large, it will generate a uniform E field over the space. Okay, for the top part, the E field pointing upward, and then for the bottom part, E field pointing downward, but the magnitude will be the same. Okay, and here we use the Gauss law, so the calculation will be like 1, 2, 3, and then to the answer already. Okay, so far any questions? Okay, so here, okay, after finishing one plate, so here we try to pick two together. Okay, so here we have two conducting plate. Okay, so these two conducting plate will have some thickness. But yeah, okay, so here it says like, okay, so this is a plate. Okay, so here we have figure A and figure B. So when you see figure A, try to ignore the y part. They are not placed together yet. So when you look at this one, just forget this one, and then the vice versa. And so here we have a positive charge plate. Okay, we have two sides. So for the left side, the density will be sigma 1. On the right side is also sigma 1. And still it is infinitely large. Conducting plate. So the charge can freely move. But if there are nothing else, nothing charged nearby, then the charge will go to the left surface and also the right surface. And yeah, as much as they are symmetric, so the density will be the same. And according to the result in the previous slide, we know that E plus generated by this structure will be sigma 1 over 2 epsilon naught. Okay, so just plug in the number. Replace sigma by sigma 1. So nothing special. And for this one, rather than having positive charge, we have negative charge. Okay, so when we see this one, so try to forget this one. Okay, so here we have a negative plate on both sides. Okay, we also assume that they have the same charge density, sigma 1. Okay, both sides they have sigma 1. Yeah. Okay, so they will generate the E field on both sides. Yeah. So for this one, this E field will point to the left side. This E field point to the right side. But here, the direction will be the opposite. So this E point to the right side, and then this E field point to the left side. Okay, but the magnitude will be actually the same. Okay, so for part C, we try to place these two structures together. Okay, then the thing is like all the positive charge will go to the right surface, and all the negative charge will go to the left surface. They will attract each other. So yeah, that's why they will. The positive charge go to the right side and the negative charge go to the left side. Okay, in this case, this new sigma, later on we will call it sigma, but it will become 2 sigma 1. Because already half of it on the left, half of it on the right, and then both of them are sigma 1, and then now all the charge go to the right side. So it will be double because the left side is 0, so the total charge density didn't change, but all the charge go to a single side. So this is 2 sigma 1, this is 2 sigma 1. So in this case, E plus E plus will be 2 sigma 1 over 2 epsilon naught. Okay, for this one, the E field points to this side for E plus, and then E plus like this. And then for E minus, all the negative charge go to this side. And here we have 2 sigma 1 over 2 epsilon naught. And then, yeah, and then the direction of the E minus will be like pointing to the plate. So E minus point to the right side, and then E minus point to the left side. Okay, so here, this is the left side, so it is E plus. This is the right side, of course, including this one. E plus should be pointing to the right side. And then for this one, E minus on the right side point to the left, and then E minus point to the right side on the left. So include this part, it is E minus pointing to the right. Okay, so this one and this one will perfectly cancel. This one and this one will also perfectly cancel. So it says on the left side E equals 0, on the right side E equals 0. Only in the middle, both E plus E minus point to the same direction. Okay, so they will add up. So E will be this thing multiplied by 2, or this one plus this one is 2 times this one. Okay, so finally E will be E plus plus E minus, which is so these 2 will cancel with these 2. So we have 2 sigma 1 and epsilon naught. And then we call the new density to be we call the new density to be sigma. So finally it is called sigma over epsilon naught. Sigma over epsilon naught. So sigma new surface charge is the new surface charge density. Okay, so this is the expression for the, yeah, so we can call it parallel plate. Parallel plate. 平行的 parallel plate. P-L-A-T-E, parallel plate. 平行板. Okay, so and in chapter 25, you will know this is actually called a capacitor, 电容. So yeah, so chapter 25 we will go more deep into the capacitor. Okay, to find some different capacitor value for different structure, like parallel plate, and then cylindrical capacitor, spherical capacitor, something like that. And even we will fill in something called dielectric inside the parallel plate, and then do something else. But at least here we can try to use the Gauss law to find the E field generated by the parallel plate. Okay, so the quick conclusion is that if we have a parallel plate placed close together, it will not generate E field on the left side and the right side. It only generates uniform E field between them. So in the slide, sometimes it will say, oh, we have generated a uniform E field, which is generated by this kind of structure, maybe in a large area. So the two players will be placed slightly far away, but but maybe in the next chapter 24, we know what is voltage. Then later on in chapter 25, you will know the definition of a capacitor is like C equals Q over V, something like that. C equals Q over V. In chapter 25, you will know that. Okay, so this is the parallel plate. Okay, so here we can see a sample problem. Okay, so it says portion of two large parallel non-conducting sheets, each with a fixed uniform charge on one side. The magnitude of a surface charge density are sigma plus for the positive charge sheet and sigma minus for the negative charge sheet. Find the electric field to the left of the sheet, between the sheet, and to the right of the sheets. Okay, so yeah. So this is easy. We only need to plug in the values to the expression we already got. So here we have two plates. This is a positive plate. This is a negative plate. So for the positive plate, it will generate the E field, pointing to the left on the left side, pointing to the right on the right side. Okay, so this is for the positive plate. And for the negative plate, it will generate the E field pointing to the right on the left side, and this is also on the left side of this negative plate. And then it will generate the E field pointing to the left side on the right. Okay. So here we only need to find out what is E plus and what is E minus. So for E plus, it is nothing but sigma plus over 2 epsilon naught. 2 epsilon naught. Okay, so we just need to plug in the number. Our E plus is 6.8 times micro is 10 to negative 6. Okay, over 2 times epsilon naught, 8.85 times 10 to negative 12. Okay, so this number is 3.84 times 10 to the 5th power Newton per Coulomb. Okay, and then E minus, similarly, we can have a sigma minus over 2 epsilon naught. Okay, for sigma minus, it is this value, 4.3 times 10 to negative 6 over 2 times 8.85 times 10 to negative 12. So this will be slightly larger than half. So this is 2.43 times 10 to the 5th power Newton per Coulomb. Okay, so here we can try to find the E field to the left and then between and also to the right, denoted by EL, EB, and ER. Okay, so here EL will be E plus minus E minus. Okay, this one is larger. This one E plus is larger. So it will be E plus minus E minus because they point to the opposite direction. So for EB, it will be E plus plus E minus and then point to the right side. And then for ER will be also E plus minus E minus and then ER will point to the right side. Okay, like this. Okay, so EL will be, EL equals E plus minus E minus, okay, which will be, 1.41 times 10 to the 5th power Newton per Coulomb, and then it points to the left side. And then for EB, it will be E plus plus E minus, okay, which will be 6.27 times 10 to the 5th power Newton per Coulomb, and then it points to the right side. And then for ER, okay, it will be E plus, also E plus minus E minus, which will be 1.41 times 10 to the 5th power Newton per Coulomb. It points to the right side. Okay, still have another page. Okay, so if